We have talked a lot about zero knowledge proofs, like Lucy just said, and now we are sitting with one of the world's foremost experts on the subject. Thanks for being with us, Justin. I was hoping that you could start off by just explaining what you do at A16Z and what the larger goal is for the cryptographic research team there.
Yeah, sounds good. This is on. So A16Z research is about 2-3 years old now. There's depending on who you count, there's like 5 to 8 of us, I guess. It's a mix of economists, cryptographers, some people who work on distributed systems and consensus. And then we also have close relationships with some political scientists who study things like on-chain governance, can kind of speed run experiments in how humans can organize themselves, that used to take decades or centuries or something like that. Formal verification people to try to get bugs out of smart contracts and stuff. So, blockchain brings in many different disciplines, and the research group kind of reflects that. So we kind of have a dual purpose. There's sort of the obvious one of if any of the portfolio companies run into technical problems, we can potentially help with that, or maybe steer the roadmap so they don't run into the roadblocks in the first place. If the investment team just needs some understanding of whether proposals they're seeing are technically feasible or not, we can help. Maybe the more interesting thing kind of externally is there's also an engineering team, about 7-ish people as well. And the research team and engineering teams work closely together to build open source tooling for the whole ecosystem. And the general, ethos is, the firm is sufficiently invested in the entire blockchain space that it's sort of going to succeed or fail, whether blockchain as a technology succeeds or fails. So if we can kind of push forward the whole ecosystem, we would like to do that. That's kind of it's both selfish and altruistic at the same time. So those are the things we work on.
Cool. So we're going to dive kind of into some deep science in this panel, so a little bit of a change from some of the other ones. But in order to do that, we're going to rewind back in time to the early 2010s. Justin, you were studying theoretical computer science in grad school, and little did you know that you were actually studying a part of a technology from the future that's called a snark. And we have that spelled out right here. Justin, what the hell is a snark?
Yeah, so a snark is a cryptographic protocol that lets any untrusted party prove that they know some data. Cryptographers often call that data the witness, satisfying some property. So I'll give maybe 2 examples. I'll start with one. Let's say you want to prove to the Ethereum blockchain that 20,000 transactions, they've all been digitally authorized by the initiator of the transactions, and they're all valid. None of them are, sending more money than exists in the initiating account and all that jazz. A snark would let anyone kind of prove to, say, the Ethereum blockchain that they actually know all those transactions and that all those transactions are valid, and that, processing those transactions kind of advances the state of the world from state A to state B. And in that way, the blockchain itself doesn't have to do all that processing. That untrusted person did, and it doesn't matter that, the Ethereum blockchain doesn't trust them because there's the snark proof, can't be forged. So succinct here just means the proof is short and fast to check. Non-interactive means it's just like a computer file that you can post on the blockchain for anyone in the world to check, or you could attach it to an email or post it on a website or something. And then argument of knowledge just means it's secure. So that, there is basically no way at all to find a convincing proof of a false statement. So if I hand you a snark proof, you don't have to trust me at all. If the proof passes the checks out, what I'm saying must be true. That's the snark.
And so you were studying, in grad school in the early 2010s, you were studying something called the sum check protocol. And we're going to come back to that in a little bit more depth, but just really quickly, what is the sum check protocol?
So I guess from today's perspective, the SumCheck protocol, I would describe it as sort of the key tool to make snarks faster. Right? It takes a really long time to generate these proofs, even if the prover is honest. So, bridging this trust gap, generating this proof that what you're saying is true, and the proof is really short and fast to check, it comes at a very steep price. And so, in my view, this is still a somewhat controversial technical view, but making progress in kind of convincing everyone. The SumCheck protocol turns out to be kind of the key to making it faster to generate the proofs. But back then, when I started working on this, 2009 or so, I didn't even know what a snark was.
Right. And so, okay, so let's put the SumCheck protocol to the side for a second and just come back to snarks, sort of generally speaking. Zcash, and we've heard a lot about Zcash today, was the first practical implementation of a snark. How big of a deal was that, in your scientific opinion?
Yeah, so I think Zcash was a huge deal because it was the first deployment, real world deployment of what I call a general purpose snark, right? So I'll give a little bit of history here, I guess. Theorists came up with the notion of actually what I was working on in 2009, something called interactive proofs, kind of a predecessor of snarks, so they came up with this in 1985. Actually, the same paper introduced the notion of zero knowledge, which has come up many, many times today, and I'll maybe say something a little bit about that shortly. 5 years later, we understood that you could prove incredibly complicated statements with very kind of short and fast to check proofs. In 1985, when the notion was put forth, the computer scientists that did it were almost acting as philosophers. They had no idea how powerful it would be. They were thinking to themselves, since for 2,000 years, since Euclid and the ancient Greeks, a mathematical proof has been something you write down on a sheet of paper or in a book, and somebody's going to check the proof step by step to make sure every little step checks out. And they ask themselves, is this really the most general notion of proof? Proof is about convincing someone a statement is true. When two mathematicians are at a blackboard, they haven't yet written out a careful static proof that's in a book or something. They might have a conversation, right? So they talk to each other. One guy's saying it's true, and the other mathematician saying it's, I don't believe you yet. So, the challenger will ask questions and get responses, and they kind of go back and forth. And, after enough questions, maybe the challenger is convinced, right? So that's what an interactive proof is. And eventually, this led to snarks. And we had theoretical snarks, incredibly efficient in theory. By 1994, okay? But as of 2009, if you kind of naively implemented a snark for use in Zcash, probably the proof would have taken trillions of years to compute for one transaction, right? So there was a bunch of progress between, let's say, 2009 and 2013, 2014 in bringing trillions of years down to for something like the Zcash statement, maybe even seconds or something. Zcash was just the first demonstration of that.
So this is we've talked about this before, sort of the role of the blockchain in the evolution of this technology. And I think at this point, we all can wrap our heads around the fact that Bitcoin and Ethereum and most other chains really are not private, and that Zcash used zero knowledge proofs to become private. And now we're hearing about how zero knowledge proofs could have benefits beyond crypto, even beyond blockchains. But I don't want people to miss something, which is that it was the emergence of blockchains around the time of this early work in snarks that you're talking about that really catalyzed what we're now calling a nascent industry focused on zero knowledge proofs. And so the question is, what do people not understand about the role that blockchains have played in the evolution of this technology?
Yeah, so I'd say so even today where there's been billions of dollars invested in making these zero knowledge proofs more performative and more powerful and getting the tooling right, we still mainly see them deployed or even being attempted to be deployed in blockchain settings. There are some exceptions, but they're few and pretty immature. So why? Why is that? And I'd say the main blockchain is sort of a perfect storm, a perfect application for snarks, zero knowledge snarks in particular, for two reasons. So one is you just need security against adversaries. It's the most adversarial setting you can kind of think of, because everyone in the world, I think of the blockchain as just a world computer. Like, everybody in the world can sort of follow along with what the computer's doing, contribute to its security, submit transactions for the computer to process, right? So everyone in the world also has a maximal incentive to attack that computer and convince it that, you own 1,000 Bitcoin instead of 0 Bitcoin or something, right? So if you're going to use, any technology in the context of blockchains, you need it to be cryptographically secure, ideally. And so snarks have that property, and it comes at a huge price, but you need that property, so you're willing to pay the price. And then the other thing is, in the scheme of things, the statements we want to prove in blockchain applications are very simple. They tend to be things like, I know the private key, think of that as a password, controlling this account, this wallet. So therefore, I am, the right person to authorize this transfer, out of this account to someone else or something like that. And that's a very simple statement compared to potential applications in non-blockchain settings. Maybe you're proving, I know a bunch of data that's been signed by someone I, think is reputable. And when you evaluate some giant ML model on this data, it spits out this prediction or something. I don't know. That's a much more complicated statement to prove. So that combination of needing the security guarantees and being able to pay the huge price that snarks come with today, because the statements are so simple. Like, the prover, for Zcash can finish in a couple seconds, even though, if you didn't have to prove the statement, it'd probably take milliseconds or something.
So it seems like kind of the case that blockchains gave this technology sort of a metaphorical foot in the door. And then once it had a foot in the door, researchers like yourself gravitated toward it for various reasons. So let's go back in time again, back to the Sumcheck protocol. Back in the early 2010s, what were you trying to do with that?
Yeah, so back then I was just looking at interactive proofs, so in particular, this K means the prover in the snark is proving it knows some data. I know a bunch of blockchain transactions, that have all been verified in some way, or I know the secret key controlling some wallet or something. Interactive proofs not really about proving you know some data. It's related. Interactive proofs are about offloading a lot of computational work onto an untrusted party, right? So actually the application we had in mind a lot back then, although it really was and still is a pipe dream, but it's like what we wrote as a story in our paper introduction, so the reviewers weren't like, this is, a waste of time or something, was cloud computing, right? So everybody goes to Amazon and they say, hey, I don't have the computing infrastructure to run this computer program on my data, so here's my data, here's my computer program, you run the program for me on your beefy computing cluster. And Amazon comes back and says, okay, I did it, and here's the output, number 42. That's what it spit out. And people were just, believing that. And, Amazon's terms of service said, we make no guarantees that, we're doing everything right, but everyone just trusted them. We're like, wouldn't it be nice if Amazon could prove that the answer they return is correct? That's what we were looking at. And interactive proofs in principle can do that. But they're, except in limited, important but very limited special cases, the Amazon would spend millions and millions of times longer to produce the proof than to just run the computer program. And no one is willing to tolerate a million-fold increase in their cloud computing bill that they pay Amazon every month. So it was and remains a pipe dream. Yeah, but it turns out that those simple special cases that the technology actually worked for back then turn out to be kind of the key bottlenecks inside snarks today. So these old papers from 15 years ago now, not quite 10, are kind of seeing a new renaissance.
So did you, when you were, you mentioned a few times that the Amazon compute example was kind of not necessarily based in the real world, and sort of, I think a lot of us have read academic papers and we kind of understand why you set it up like that. Did you ever think there was a possibility that could become real? Did anyone ever try to get you to commercialize it back then? This is still kind of pre when you realized that this would apply to snarks.
Yeah, so I mean, people would ask sometimes, for the applications where the performance like actually looked good back then, should you try to, start a company or something? And I was like, no way, like this is just too special of a case, and no one's going to really care that much about, people just trust Amazon and it's fine. Some venture capitalists reached out to me, it must have been 2013, and just asked me, like, do you see a future for this technology? And I'm like, no. And so 2013, I didn't really know. I probably had heard of Bitcoin, and that's about it. Didn't really know what was up with it. That's about the time Ethereum was coming out, so maybe, I just wasn't in the know. But so 2013, no, I just thought, I was just wrong. I just thought no applications for this. By then, I knew what a snark was, and I still thought no applications for this. So the blockchains really, were the launch pad for this to actually see use. And now, 10 plus years on, it's kind of going to be one of blockchain's gifts to society at large, because this is going to get performative enough and secure enough, and I can say more about the challenges there, that it'll kind of just eat the world. And maybe one more comment. Like I said before, this whole thing started with interactive proofs, where some theorists were asking themselves, like, what is the most general notion of proof, like humans use to convince each other a statement is true. They were almost acting as philosophers. And it took like 5 years to figure out in theory that these interactive proofs actually are way more powerful than we could have expected, and then another 5 years for like the notion of snarks to really be put forth. And then, 20 years until they maybe became practical. And it'll take, 20 years, years after that to really become mature, right? And so in the end, it'll probably have been, it's 40 years already, probably will be like maybe 45 or 50 when this really finishes maturing. And it'll like be a triumph of human imagination and intellect. I think maybe up there with, the triumphs of, discovering the Higgs boson, maybe even, nuclear fission or something, right? Like it started from almost philosophy to, and it's hard to predict what it'll be used for, but as kind of I have a researcher's faith that when something kind of starts from philosophy and then you realize it will, can actually go out there in the world, it sort of takes on a life of its own, and it'll really make a difference.
What was it that turned the light on for you that the subject protocol would apply?
So, I spent the first, 5-8 years of my career, like kind of not in snarks, right? It took 2017 was when we realized like you can take the subject protocol and take some cryptography and put them together to get a snark. So that was 7 years ago. And that's when I started looking at all of the other snarks that, like in Zcash was using and stuff like that, and being like, well, what if they use the subject protocol? Oh, it gets much better, much simpler, much more performative. And so for the last 7 years, I've read like every paper with the subject protocol in my head. And, often it's the case that if you kind of really have internalized how powerful this hammer is, you can kind of throw away half the paper or something. And, it's sort of a unique perspective. And I think it might be why it's been a little hard to convince other researchers kind of the veracity of, my positioning. To have looked at the entire development of the technology for almost a decade with this one tool, in mind, it sort of gives you a unique view. So I've just kind of followed everything, and it's always like, this hammer works, over and over again. Yeah.
Right. You did tell me once that the subject protocol is like a hammer and everything is a nail, which I still don't quite understand. But the subject protocol, and you said this earlier, you're working on making an aspect of this faster, right? And that kind of draws the attention back to the S in this acronym, succinctness. And can you tell me sort of how has that changed? How has zero knowledge proofs changed the blockchain space in the succinct way? Because we've been talking about privacy all day long.
Yeah, okay. So let me say quickly something about ZK versus succincts, because they're different things. Unfortunately now, people tend to use ZK to as a catch-all, often they mean succinct and they say ZK. So this can be very confusing if you're trying to learn more about snarks or ZK, just FYI. So ZK is a privacy property. It's the proof reveals nothing about this data that the prover is claiming it knows, other than it knows the data. Okay, so you need, like, if you want to prove, the private key controlling some, Ethereum wallet, right? Like, you don't want to leak any information about that private key because then somebody's going to steal all of your ETH or something. You want to prove, that password, that secret key, but not reveal any information. That's what ZK gives you. Okay. To date, actually, snarks have been more important, not for ZK, but for the succinctness. And this is the example I gave before, which basically captures what's called a layer 2 rollup. But you kind of treat the blockchain almost as like, in this Amazon, verifying Amazon. It's like the blockchain is the verifier, and anyone out there in the world is Amazon, right? So, anyone out in the world can process a whole bunch of transactions and just prove to Ethereum, prove to the blockchain that they process the transactions correctly. And that way, all the blockchain nodes just have to check the proof. They don't have to process the transactions themselves. So Ethereum has actually kind of redesigned its entire plan for the future around exactly this. And kind of, in the extreme, perhaps in the future, like the only thing Ethereum does is like verify snark proofs, and like all the transactions really get processed on these layer 2s. Okay, and actually, I think something we've talked a lot about, Zcash today and privacy projects, because this is like privacy event. But really, most of the privacy projects are nascent, and just we're seeing them come online now. There's been Zcash and Tornado Cash that have been high profile, Monero, and that's about it. So this is actually part of my concern for where we are policy-wise. Like the world is sort of just figuring out, or not even, how to do policy for blockchains without privacy when everything is just public, right? And it's sort of been okay to not tackle privacy yet because we haven't really had much privacy. Maybe Tornado Cash and Zcash, big exceptions. That's changing pretty soon. So kind of we have to start doing something, or we're going to have an issue. Anyway, so that's where succinctness is. Just move all that hard work off chain. The blockchain can basically just check the proofs.
Right, and I think you're working on something called Jolt, which you can explain. But if I'm understanding correctly, sort of looking forward, the goal is now to really focus on the S and make it easier and more efficient and faster to make more complicated arguments of knowledge and even prove that you're doing some complicated things with other computers. Can you just fill us in on sort of what you're focused on with Jolt and what a ZKVM is?
Yeah, sounds good. So this will sort of give a quick overview of like where this snark technology is today and where, how I think it's going to evolve going forward. So let me just think where it is. So we've actually had for a very long time, even I think the first snark in 1994, the succinctness was pretty good. Right, like the proofs would be pretty short and pretty fast to verify. The real issue was like the prover was too slow. Like you would just never get the proof to be checked in the first place. So my work has sort of focused from the start. The sum check is really all about making the prover faster for the most part. Okay, so I'd say snarks really have three main technical issues that still today. So one is this like prover time is still pretty bad. Okay, it takes a lot of compute power to generate these proofs, and you're waiting around a while to boot. The next is they're very complicated, and they're full of bugs. And if there's any little bug in the snark, it's really, the cryptography is not really securing anything. It's secured by obscurity. Like you might need a PhD to find the bug, but it's not, that's what's securing it. Like if you had the PhD and you spent enough time, you'd find the bug, you'd break the system, you'd produce convincing proofs of false statements, and the snark is it's actually actively damaging because people are trusting it and it's actually not providing what they think it's, providing. And then the final issue is they're really hard to use. So up until very recently, the way people use snarks is every time there was a new application, it was kind of like writing computer code in the 1960s. Probably even worse. Back then you had punch cards and, you're writing like very low level, like move this value to this register. You had like, I don't know, 32 registers and you were individually by hand controlling what data is in what register. That's what it was like with snarks until very recently. So now there's a move to something called ZKVMs. The idea is that developers will not have to know anything about how snarks work, right? If you want to use a snark in a new application, you will write a computer program in whatever computer programming language you like that takes as input a claimed witness and just checks that the witness satisfies the property you're claiming, right? And then you say, prove. And this ZKVM thing, I'll tell you what that is in a second, will just handle the rest for you. And so, it'll democratize ZK. You won't need a PhD to use the tech. And that'll be great. Okay. So what is ZKVM? It is a snark that lets a prover prove it correctly ran a computer program. Specifically a computer program expressed to run on like a very simple machine. That's what like the VM means. And the V is virtual machine. And so the machine is so simple that it's like, it's not a machine necessarily that you would actually build. It's virtual, right? So it's like you will run the prover on your laptop. It will prove it correctly ran this computer program that was actually written for another much simpler piece of hardware than like the ARM or Intel chip inside your laptop or something. Okay. All right. So ZKVMs, I think the community is now pretty convinced like this is how things will go. The problems are they're incredibly complicated and they're incredibly slow for the prover. So, they address kind of the usability issue with snarks. You don't need a PhD to use them anymore, but they're definitely full of bugs, so they're not secure, and the prover's still slow. So Jolt is a kind of a new kind of sumcheck-centric way to build a ZKVM. And I think the prover will be noticeably faster than the pre-existing ZKVMs. And I also think it's simpler. And so like my PhD, interns this summer were focused on formal verification. And this is like the Ethereum Foundation is putting $20 million into these sorts of efforts now. This is trying to like make totally certain that there's no bugs, right? And so my prediction is that in the next couple years, like snark prover performance will reach a point where you can actually apply them in all sorts of applications. It's really not there today. Okay, but we're very close, like 2 years max. But then the next thing will be they'll just be full of bugs, and so you're still not really they won't reach their potential until we get past that. That will take longer. That's minimum 3 years. Could be more than that. So yeah.
So there's a lot of science that still needs to be done. It still seems like we're kind of early in the development, actually, even though it's already achieved so much as we've talked about today. And this is the Privacy Summit. So for the last question I wanted to ask you is, how should we think about the implications for privacy of all this? You're talking about things being possible in 2 years that sound like science fiction. What does that mean for privacy, and what does that mean for policymakers that are concerned about this?
Yeah, so I think it means a lot. I think a couple of the things it means have already been discussed a bunch today. So I mean, if we're focusing on blockchains, for a second, maybe I can say a little something beyond that. Blockchains, they cannot reach their potential if everything is sort of public, right? Like we cannot move the entire banking system into a situation where everyone's bank accounts are public and everyone sees who's sending money everywhere. Like that just won't work. And I think one of the few products that have actually found product market fit in blockchains today is stablecoins. I think they've been mentioned a couple times today. This summer with our PhD student interns, probably a disturbing statement about the U.S. None of them were American. They're from all over the world. They go out socially and they could not like reimburse each other for covering dinner or something. They tried with Apple Pay. The money just like went into some abyss and like I'm pretty sure it never came out. But with some USDC stablecoin, no problem, right? So seeing that, it's like it's clearly not going to go away, right? But you're never going to use stablecoins for getting paid your income. Companies will never pay their suppliers or whatever if that's private at all. Yeah, so we're just going to need some privacy for blockchains to reach anything like their potential. What I can say a little bit more about is kind of the technical side of things. So I guess I'll make two clarifications maybe. Okay, so one is compliance, with ZK to get privacy in blockchains. Doesn't have to be like worse because there's privacy preserving cryptography there. It actually can be better, right? So like I was reading like the TD Bank case recently, $4 billion fine. And what happened, I guess, was they just stopped investing in their compliance, their AML program, right? And so like the way compliance is done today is there are humans doing it, and you have to continuously invest in that. And it's not public, like if that investment is happening. And so, I guess if it doesn't happen, and maybe, I guess there might be incentives for it not to happen, I suppose, since it's happening. Maybe you try to clean it up after the fact. With ZK and blockchains, the compliance is programmatic and it's publicly visible. Like this smart contract will only accept proofs that prove that some compliance check is satisfied. Right, so like there's no ongoing investment in perpetuity to otherwise you lose the compliance. There's no like opaqueness where you can't tell what's going on until something horrible happens. So it actually can be better. The downside is there's no human in the loop, right? Like you have to decide like what is compliant and what isn't, and then your smart contract, maybe you can update the smart contract, maybe not, right? So it cuts both ways. But if we do it right, it could be better. Are we going to get it right? I don't know. It's very hard to say. And then the other thing I'd point out, because it might not be clear, is there's a lot more to building privacy into systems than just having a zero knowledge proof, right? I could hand you a zero knowledge proof from 10 years from now. It's formally verified. We know there's no bugs. The prover's super fast, and it's still not clear what's the right way to build like a private and compliant system, right? And like, so Alio is here today, right? They recently launched their mainnet. I'll wrap this up. It's not like, if someone handed Alio as zero knowledge proof, 3 years ago, they would have been like, okay, we're done, mainnet, boom, right? Like it took 3 years of building. And what's going on is, I'll give 2 examples and then we're done. So if you want to build like a world computer with privacy, there are loads of questions about, well, what's going to actually be kept private and what's going to be public, right? If literally everything is private, no one can do anything. I don't know anything about you. You don't know anything about me. How are we going to, transact if I don't know what you have to give me and you don't know what I have to give you or whatever? So, there's all sorts of technical questions that do not have clear answers. As another example, Zcash was, an incredibly early and incredible piece of technology, but like it has downsides, right? Everyone in the world who wants to transact in Zcash, they have to monitor every Zcash transaction that is ever sent in the whole world. And so every time there's a new transaction, they have to look at it and see, do I own this new coin? Did someone send this coin to me, right? They have to look at each and every coin and test, is this for me? Is this for me? Is this for me? And so there are other ways to wield the zero knowledge proofs that might not require that, right? So it's not like you give me the zero knowledge proof and the technical problems are solved, right? There's a whole other technical issue of what you actually do with the zero knowledge proofs. And so that makes it very hard to predict, but that's why we're all here, I think, to try to make sure we get it right. So.
Thanks a lot, Justin. I really appreciate it. And yeah, we're at time, so that's going to be, do we have a coffee break next? Okay, we actually have another session. All right, thank you very much, Justin.
Thanks for having me.